Hey everyone, welcome back. This is lesson 11.3, independent and dependent events. The objectives for this lesson: by the end of the lesson, you'll be able to determine whether events are independent or dependent. You'll also be able to find the probability of independent and dependent events. Your vocabulary for today is independent event, dependent events, and conditional probability. Events are independent if the occurrence of one event does not affect the probability of the other. So for an example, if a coin is tossed twice, its landing heads up on the first top and landing heads up on the second toss are independent events. The outcome of one toss does not affect the probability of heads on the other toss. To find the probability of heads twice, multiply the individual probabilities. So you can see the probability of getting a heads the first time is 1 out of 2, and the second time it's also 1 out of 2. So the total probability is 1 out of 4. So the probability of independent events: if A and B are independent events, then the probability of A and B is equal to the probability of A times the probability of B. So there's your formula. So let's take a look at an example. A six-sided cube is labeled with the numbers 1, 2, 2, 3, 3, and 3. Four sides are colored red, one side is white, and one side is yellow. The first probability we're going to find is tossing 2 and then 2 again. So first of all, we want to realize that tossing a 2 once does not affect the probability of tossing a 2 again. So the events are independent. All right, so we're going to use our formula, and now we notice that 2 of the sides are labeled 2. So the probability is 2 out of 6, or 1/3. So we're going to say 1/3 times 1/3, and that would equal to 1/9. Okay, so each of the probabilities of getting a 2 would be 2 out of 6, which is equal to 1 out of 3. And then we just multiplied it twice and got 1/9. All right, here's another example. This time we're going to find same cube, but this time we're going to find the probability of tossing red, then white, then yellow. Okay, so the results of any toss does not affect the probability of any other outcome. So we're going to be multiplying each of our probabilities. So we have to find the probability of getting a red, the probability of getting a white, and the probability of getting a yellow. So it tells us that 4 sides are red. So our probability of getting a red is going to be 4 out of 6. The probability of getting a white, there's one side that is white, so that's going to be 1 out of 6. And then yellow, we see that there's one side that's yellow, so again, that's 1 out of 6. So we are supposed to be finding the probability of getting a red, then a white, then a yellow. So we're going to multiply all those together. 4 6 times 1 6 times 1 6, we get 4 over 216, and that equals 1 out of 54. Okay, try a couple of these two on your own. Turn your video off and give it a try. All right, the first one, we're dealing with a number cube, and we know there's 6 numbers on there, and they want to know what's the probability of rolling a 6 on one cube and then 6 on another cube. So the probability of getting a 6 is a 1 over 6, and then a 1 over 6 the second time. So that's pretty easy. 1 out of 6. 1 out of 6 equals 1 over 36. All right, the next time we're tossing a coin, we want to find out about tossing heads, then tails when tossing a coin 3 times. So the probability of getting a heads the first time is going to be 1 over 2. The probability of getting a heads the second time, still 1 out of 2. And then tails the third time, still 1 out of 2. So we're going to multiply all those together, and we end up with 1 out of 8. All right, events are dependent events if the occurrence of one event affects the probability of the other. For example, suppose there are 2 lemons and 1 lime in a bag. If you pull out 2 pieces of fruit, the probability changes depending on the outcome of the first. All right, so let's look at this tree diagram. It shows the probabilities for choosing 2 pieces of fruit from a bag containing 2 lemons and 1 lime. So we can see if we chose a lemon, our probability would be 2 out of 3. Now, there's only one lemon left in the bag, so the next time the chance of getting a lemon is 1 out of 2, and getting a lime, the chance is 1 out of 2. Same way if we chose a lime the first time we have a probability of getting a lemon of 1 out of 3. But the second time, there's no more limes in there if we picked the lime, but if we didn't, we still have a chance of getting a lemon. That's our only chance, is a 1 out of 1, so 100% chance. Okay, the probability of a specific event can be found by multiplying the probabilities on the branches that make up the event. For example, the probability of drawing 2 lemons is 2/3 times 1/2 equals 1/3. So let's put this in mathematical terms. To find the probability of dependent events, you can use conditional probability. So the probability of event B given that event A has occurred. So here's your formula right here, and we're going to actually go ahead and do some problems with that now. Here's an example using conditional probability. We're given the example that 2 number cubes are rolled. One is red and one is blue. And we're to explain why the events are dependent. Then we have to find the probability that one red cube shows a 6 and the sum is greater than 9. All right, so step 1, we need to explain why the events are dependent. So remember, events are dependent if the occurrence of one event affects the probability of the other. So first of all, if we roll a red cube and a blue cube, we're going to have 6 different chances of the red cube having a 6 on it. So that's an easy probability, 1 out of 6, reduced down. And next we need to find the probability that that red 6 will also have a sum greater than 9. So let's just talk about how we had 3 of those. I could get a red 6 with a blue 1, and that sum is only 7. I could get a red 6 with a blue 2. My sum would be 8. Red 6, I'm going to go ahead and write all the 6s down. And with a blue 3, 4, 5, or 6. All right, so my term would be 9, 10, 11, 12. So I actually have 3 of them, but would end up with a red 6 and a blue number that would give me some greater than 9. And so that probability would actually be only 1 out of 2. 3 out of the 6, 1 out of the 2. So that tells us that the events, the red cube shows a 6 and the sum is greater than 9 are dependent, because the sum being greater than 9 is different when it is shown that it has a red 6 that has occurred. So these two numbers aren't the same, so we know that these are dependent events. All right, so finally, step 2, we're going to find the probability of rolling a red 6 and that the number is greater than 9. So the probability of rolling a red 6 we determined was 1 over 6, and the probability of rolling a red 6 that had a sum of greater than 9 we saw was 1/2. We multiply those two probabilities together and we end up with 1 out of 2. Let's do another example using conditional probability. In this case, the question tells us that 2 number cubes are rolled. One cube is white and one is yellow. We are to explain why the events are dependent and then find the indicated probability. So the indicated probability is that the yellow cube shows an even number and the sum is 5. All right, well, first we know that the events are dependent because the probability of the sum being 5 is different when the yellow cube shows an even number. So we know that there are 36 different outcomes and 18 have a yellow even number. So that probability is going to be 18 out of 36, and we can reduce that to 1/2. And that probably seems pretty reasonable to you. The next thing we need to do is notice that 18 outcomes that have a yellow number 2 have a sum of 5. So that probability is going to be 2 out of 18, and that reduces to 1 out of 9. So now to solve this problem, we have to say that when the probability of yellow is even and the sum equals 5, we can see that the probability of even number times the probability of the sum is 5 and a yellow even number. So it's going to be 1/2 times 1/9 equals 1 out of 18. All right, so turn your video off and try this one on your own. This problem says 2 number cubes are rolled, one red and one black. Explain why the events are dependent and then find the indicated probability. So the red cube is going to show a number greater than 4 and the sum is going to be greater than 9. So step 1, of course, we want to explain why the events are dependent. So of the 36 outcomes, 12 have a red greater than 4. All right, so that probability is going to be 12 out of 36 or 1 out of 3. Next, we want to show that of 12 outcomes with a red number greater than 4, 5 have a sum greater than 9. So here we have 5/12, and we can see that those two are not the same, so these must be dependent. And the events the red cube shows greater than 4 and the sum is greater than 9 are dependent because the sum greater than 9 is different when it is known that the red cube that shows a number greater than 4 has occurred. Step 2 is to find the probability. This is pretty easy multiplication. Now we're going to take the probability that it is a red and greater than 4, and the probability that the sum is greater than 9 and the red is greater than 4. Multiply those together, and we end up with 1/3 times 5/12 equals 5 out of 36. All right, conditional probability often applies when data fall into categories. All right, so let's use a table to learn more about conditional probability. In this case, we're going to be talking about immigrants and immigrants. And just in case you don't know, if you are an immigrant I if you have come into a new country. You are an immigrant with an E if you are leaving your country. So depending on where you are coming or going determines whether you are an immigrant with an I or an immigrant with an E. So just a little interesting tad bit there. All right, so let's get going with this. So the first probability that we're going to find is that an immigrant is from the West. So the first thing we want to look at is find out all of the immigrants. And so we're going to look at our whole entire column here. And we want to choose the one from the West. So we're going to choose this one. All right. So we're going to end up with 2,654 out of the total number of immigrants. All right. For the second one, it says, what's the probability that someone selected from the South region is an immigrant? Okay. So since it says from the South region, we're going to choose the South region here. And we want to choose an immigrant with an I. So we want to choose this one. So we're going to add up our total South. That's the total from the South of 8,285. And we are picking 5,042. So that is our probability that the immigrant is from the South. So you got to really read these carefully to get them correct. Our last problem is a little bit more challenging because we need to select someone that is an immigrant with an E and is from the Midwest. So the first thing we want to do, let's just talk about the one from the Midwest. So it's going to be an immigrant. Out of the immigrants, it's going to be just from the Midwest. All right, so use the immigrants column. And when we add all those up, we get 11,656, and we have 2,951. So here's our ratio to be a Midwest immigrant. Okay, now we also have to deal with this part where it says just an immigrant. If the first person I choose is an immigrant, we're going to have to take the total number of people, and then we're going to have to choose our second part. So there were 23,311 total people, and of those, then we have to add up all of our immigrants. So that's 11,656 times the probability of getting a Midwest immigrant. So once we do that, then our probability is really lower. There you go. All right, so here's one for you to try on your own. Turn your video off and give it a try. All right, so on this probability, it asks us to find the probability that a voter from Travis County voted for someone other than George Bush or John Kerry. So this is a relatively simple probability to find because there's not "and" in there. So all we're looking for is voters from Travis County, and we see those right here. And 5 of them were the other. So we're going to total up our total Travis County, and we're going to be dealing with this 5. So we'll say of the total 5 out of 148 plus 197 plus 5, divide that and you get 0.014 or 14 thousandths. All right, so turn your video off and try another one. This one's a little more difficult because it's going to have this "and" in here, so we're going to have to be multiplying 2 probabilities together. All right, so let's take a look at this. I'm going to go ahead and pull everything up here for you to look at. All right, so here it says a voter was from Harris County and voted for George Bush. So first of all, we need to find the probability that someone was from Harris County. So we're going to take the total amount, and we're going to also take Harris County. So that is this piece right here. When you add up all of Harris County and divide it by the total number of voters, we get this ratio right here. 1,058 divided by 3,125. Now we want to know the ratio of Bush to Harris. So we're going to take a look at Harris County again, and we're just concerned with those that voted for Bush. So that's going to be 581 divided by 1,058. And we multiply those 2 probabilities together and we get 0.186. I know that can get kind of confusing, so you might want to turn your video off and just work on that on your own. In many cases involving random selection, events are independent when there is replacement and dependent when there is not replacement. So let's talk about, just as a remember, a standard deck of cards contains 4 suits of 13 cards each. The face cards are Jack, Queens, and Kings. All right, so here's an example determining whether events are independent or dependent. 2 cards are drawn from a deck of 52. Determine whether the events are independent or dependent and then find the probability. So our first probability we're going to find is the probability of selecting 2 hearts when the first card is replaced. So let's remember what replacing it means. If you replace the first card, means that the occurrence of the first selection will not affect the probability of the second selection. So the events are independent. All right, so the probability of getting a heart times the probability of getting a heart is going to be the same. And so 13 of the 52 cards are hearts. So we know that 13 out of 52 times 13 out of 52, so our probability is 1 out of 16. So that's not too difficult. Our second one says, what is the probability of selecting 2 hearts when the first card is not replaced? So not replacing the first card means that there will be fewer cards to choose from, affecting the probability of the second selection. So the events are dependent. So we want to take the probability of getting a heart times the probability of getting a heart after the first card was a heart. So there are 13 hearts, 12 hearts, and 51 cards are available for the second selection. So here's our numbers. The first time is 13 out of 52. The second time is going to be 12 because we already took 1 heart out of 51. So there were only 50 cards now. So now our probability is 1 out of 17. So here's a third example. Suppose a queen is drawn, is not replaced, and then a king is drawn. So not replacing the first card means that there will be a fewer cards to choose from, affecting the probability of the second selection. So the events are dependent. So we want to find the probability of choosing a queen and then the king after the first card was a queen. So the probability of getting a queen is 4 out of 52 because there's 4 queens. And then the probability of getting a king, since we didn't choose a king the first time, but there are now only 51 cards because we have the queen already pulled, we multiply those 2 probabilities and we get 4 out of 663 is the reduced of that. So there you go. Okay, try this one on your own. Turn your video off, and I really encourage you to try this one on your own because seeing me do it and you thinking it through are very, very different. So give it a try. Okay, so in this one it says that a bag contains 10 beads, 2 black, 3 white, and 5 red. A bead is selected at random. Determine whether the events are independent or independent and define the indicated probability. So the probability is of selecting a white bead, replacing it, and then selecting a red bead. So we can tell just from that replacement, replacing the white bead means that the probability of the second selection will not change, so the events are independent. All right, so this one's pretty easy. The probability of getting a white is going to be, let's see, 3 out of 10. The probability of getting a red is 5 out of 10, so 15 out of 100, which reduces to 3 out of 20. All right, so here's another one to try on your own. Same bag of beads. Turn your video off and give it a try. All right, so on this one, you are selecting a white bead, not replacing it, and then selecting a red bead. So first of all, let's realize that by not replacing the white bead, the probability of the second selection has changed, so the events are now dependent. So we're going to figure out our probabilities. The probability of getting a white bead times the probability of getting a red after not replacing the white. So the probability of getting a white remains 3 out of 10, and the probability of getting a red, if the first one was white, we still have 5 red in there, but now instead of having 10 beads, we only have 9 beads. All right, so that's where our big change is. When we multiply those together and reduce, we end up with 1/6. All right, so one more to try on your own. Again, we have the same bag of 10 beads, and you're going to be selecting 3 non-red beads without replacement. So turn your video off and try this one. All right, so on this one, by not replacing the red beads, the probability of the next selection has changed, so the events are dependent. So the first thing we want to decide is what was the probability of getting a non-red? Well, there were 5 reds, so that means our probability of getting a non-red is 5 out of 10. Now, we didn't get a red the first time, and we kept the bead out. So now there's still 5 reds, but there's 4 out of 9 that we could choose from that will be non-red. And then again, the third time will be 3 out of 8. All right? So I hope you understand that. And when we multiply those all together, we end up with a reduced fraction of 1 out of 12. So that is the end of the lesson part. I'd like you to turn your video off and try this little short quiz because these are pretty difficult. Not that their math is that hard, but just that the thinking part of it, which is what I really want you to do. So turn your video off and try this for a second. Okay, so the answer to number 1, I hope you found, was 2/9. Sorry, I put it in the middle there. And the last one is the probability of getting a blue, then a blue, is different when it's known that the blue sock has been picked. So your answer would be 14 out of 95. If you didn't get that, you probably should practice it again and see if you can figure out how to get that correct answer. All right, so the third question has 2 parts to it. Turn your video off and make sure you can get these. All right, the answers to that, the first one is independent, and the probability is 9/169. The second one is dependent, and that probability is 11 out of 221. So again, if you didn't get these, why don't you turn your video off and see if you can work on that a little more. Otherwise, that's the end of today's lesson, and I hope you learned a lot, and I will see you next time. Have a great day. Bye.